Welcome back to another teardown. I have here on my bench a very old telecommunication box, a Siemens Attane i210. I have a rough idea what that thing did in the past, but I couldn't find any documentation regarding it. Anyway, enjoy! The front is really plain. I think these are transparent parts for LEDs, hopefully LEDs behind them. So we have power, we have assist, so system, then X21. That's a synchronous serial interface, LAN, SDSL, so symmetric DSL, and then 4 LEDs, BR1, BR2, BR3, and BR4. I think these are either ISDN S0 channels or analog telephone channels. As I said, I'm not quite sure. Both sides of that thing are absolutely unremarkable. On the back we find everything the front promised, plus some more things. So we have here a symmetric DSL, obviously an input from your telecom provider. Then we have a LAN port, output I guess, so internet over SDSL. We have this big clunky X21 D-type connector. As I mentioned, this is a synchronous serial interface. And I think you can use it to program the thing or something. And then we have 1, 2, 3, 4 ports, either analog telephone or S0 ISDN lines, plus a power plug. There's nothing on the top but some ventilation slots. On the bottom we have more ventilation slots and some more stickers with information. So it's a Siemens Attane i210 with 4 SOP. Whatever SOP means. If you know what it means, please leave a comment. Then we have here, that's just the internal type number up to the X211, and that -7 is the version. No idea what NZ+/03 means. Maybe the production date, 2003, whatever. Serial number, I guess, and it needs 48 volts DC at 1.1 amps. And it could have software option. Again, the type number repeated and the serial number repeated as barcodes. This whole big box only weighs 1,305 grams or 46 ounces. So there's really mostly air inside here. I know some bigger YouTuber than me always states, don't turn it on, turn it apart. But I really want to see the LEDs. Can I get that in there before I destroy it? And this this is a locking power plug, so you really have to lift that up here again to remove it. That's really, really neat. They don't make such things anymore. Okay, let the light show begin. And I see absolutely nothing. Okay, that's a disappointment. Did I do anything wrong? No, I didn't do anything wrong, because there's an LED here, black on black, from the power supply unit. And the power supply unit obviously also died. Okay, dead as a dodo. Let's take it apart. I'm pretty sure that there are no screws under the feet because there is only air. And it's a Siemens, of course. But there's a little detail. There's a little label here that says unlock. So I have no idea how. It says press in this direction. Okay, I need another camera position. I'm getting a little bit frustrated. I fumbled around here for quite some while and I feel something, yeah, sticking there, but whatever I do, nothing happens. So I guess we will have to go destructive. Oh no, it worked. At least I got the feet off in one piece. That's something. Okay, almost one piece. Still asking myself how we should unlock the thing. Ah. Oh. Starting to come apart. Okay, that was definitely sounded like a snap-in. Let me change the camera perspective. So I'm just going in here, pressing this forward, and then I lever the whole thing apart, which is extremely hard to do. Sorry if I'm going all over the place. Okay, another snap. The other side. And I stick something in here at the back, just so the fruits of my labor were not for naught. Okay. That's not what I wanted to destroy. Ouch. I need more tools. If you can't see blood, look away. And I have no idea how the snap-in mechanism is supposed to work, or maybe all that plastic is so old and stiff that it wouldn't come apart anymore. Sorry. This should, in theory, come apart. Oh, okay. It came. The whole plastic is just very old and stiff. Am I still somehow on camera? Yeah. Okay. Knack. And we are in. First thing to note is that the lid is dirty, but also metallized for shielding purposes, I guess. And in theory, you just have to push back these latches here a little bit and it should come apart, but it's too old. And then we have this. Ooh, a whole lot of chips, and yeah, that's a power supply unit, dual voltage, but we have a look at that in a second. No, this is a lot. This is a lot. But I want to point out here before we get the board out, the front plate and the back plate are made of aluminum. And I think the front plate is not some thin aluminum, but that's easily 2mm aluminum. And the back is easily at least 3mm. Yeah, this is sturdy. It's a shame that the plastic didn't age too well. Let's get out the main board. There are not too many screws. Okay, this is out of frame. Sorry for that. So 1 and 2, my arm is in the way as always, and 3 and 4, and this is hopefully that's soldered on, yeah, but I should be able to just, it's a quick connect to get that off. I think it's a quick connect, maybe I'm wrong. So let's remove that nut here. From the looks, they use 2.5 square millimeter cable here for the mains earth connection. That's just a wee bit of an overkill if you ask me. Okay, and now I should be able to easily, not quite as easily, but get the board out. Maybe with the whole back plate. Let's see. Yeah, it comes off with the back plate, so of course there are more screws on the front. 2 more to be exact. So this should be a good enough fit. Yep. And the back plate comes off. I was a bit off in regards to the thickness of the plates, maybe optical illusion, but that measures out to exactly 2 millimeters. And that one is also 2 millimeters. And both have some conductive gaskets all around to make that thing really tight for electromagnetic waves. The board is really enormous and there are a whole bunch of chips. Fortunately, there is not much here on the back side. There are a few interesting components here and these 4-pin jobbies. Anyway, so SDSL comes in here. This is probably the isolation transformer for the SDSL lines, and this is all SDSL related. And then we have here, you cannot read it, but we will zoom down soon enough, Xilling Spartan, who does the heavy lifting. We also have here 2 DSPs on that side, which are probably feeding the 4 ISDN or analog outputs here. We will see what is what when we have a look at these isolation transformers here for these lines, if they are for analog telephone or ISDN. There's a quartz. This also looks like a quartz. Here's another isolation transformer for the Ethernet port, and yeah, maybe that's the Ethernet controller, and that stuff is a controller for the X21. Yeah, and a power supply. So a power comes in here. This looks like an inductor, big ass for filtering. And then this is somehow bridged towards here where we have another inductor for filtering, a capacitor. And then it goes into this huge DC-DC converter. The LEDs, this almost looks like another linear regulator. Maybe they need also 1.8 volts somewhere. Doesn't matter. We will zoom down. So this Power1 48 IMS 30-0503-9G is a beast of a DC-DC converter. Okay, you can read for yourself, but input voltage 32 to 75 volts, output 5.1 volts at 4.5 amps and 3.3 volt at 6 amps. No minimal load required. And SD is basically an enable pin, which you can use to switch the thing on and off from the primary side, or you can connect that via a resistor to VN minus, and then you have a low voltage lockout. Meaning if your input voltage goes beyond a certain limit, the thing will switch off. W is a pin you can connect several others of these together, and then every single one will run with the same clock, with the same oscillator frequency internally. That's obviously good for EMI reasons, electromagnetic interference reasons. And trim, you can use resistors to voltage out 1 and voltage out 2 to manipulate the output voltages plus minus 10%. And go is not go, but ground out. The big capacitor and the big inductor here, these are recommendations from the datasheet, again, to comply with EMI stuff. Let's have a look at that block here now, because it says digital signal processors. These two are Texas Instruments TMS 320 VC 5402 digital signal processors, and they feature 2 or more external 16-bit buses, a 40-bit arithmetic logic unit, and a 17 by 17 bit one-cycle multiplier, a parallel multiplier in combination with a 40-bit adder. Fixed point everything, no floating point stuff here. 4K by 16-bit ROM and 16K by 16-bit dual access RAM. And supporting these, we have 2 Samsung K6R4016V1D-3C10 static RAM, 265K by 16-bit. I had to turn around the board so we can read the numbers here on the supporting characters. The larger one here, that's simply a 74 LVT244A, a 3.3 volt octal 3-state buffer line driver, driving obviously some lines around here. And that's a Max 708S, a 2.93 volt precision voltage monitor with a reset output and everything, probably to monitor the supply voltage for our DSPs. Now, let's move down here towards our telephone connections. The first thing you note is that you could basically double the number of parts here, at least some parts, indicating that you could really have 8 ISDN or analog telephone outputs here. So let's have first a look at these 2 supporting characters here and then progress to the next row. In a supporting role, we have a 74 ABT 125C. That's a 5-volt chip, a 3-state quad buffer. So buffering some data lines coming down here from our DSPs, I guess. And here, that's an LM339M, a quad voltage comparator. Works in a voltage range between 2 and 36 volts, a quite high voltage part, so I guess it somehow belongs to our power supply. Yes, I know, the part numbers are sideways, but anyway, we have here 1, 2, 3, 4 74 ABT 244Cs. That's the 5-volt version of the A we already saw down here somewhere. So these are 5-volt 3-state octal buffer line drivers. Then we have that little jobby here, that's just a 74 ACT04, so a 5-volt hex inverter. The bigger one here, that's a 74 LVTH16244. That's a 3.3 volt, again, 3-state 16-bit buffer driver. So a lot of data going down here at a 3.3 volts, but also some 5-volt lines going on. And finally, we have that thing, and that's probably an oscillator. Why? because that very similar looking thing here has clearly written 4 megahertz on it. So that's also an oscillator. In the next row we have 1, 2, 3, 4 Infineon PEB2068H. These are, drumroll, ISDN subscriber access controllers. So these 4 things talk with the 4 ISDN ports at the back of the thing. And that here is an Infineon PEB2025N. That's a quad ISDN high voltage power controller. So that thing uses directly the 48 volts coming in to supply these 4 with enough juice to drive ISDN lines. Finally, we are driving these 1, 2, 3, 4 ISDN isolation transformers from VAC. Don't bother looking up the part number or data sheets. And then between our ISDN connectors and the transformers, we have 2, 4, 6, 8 of these little jobbies. These are ST Microelectronics TPI Attanes. They just contain a bunch of TVS diodes to suppress any voltage spikes above 80 volts on the ISDN lines. That was this half of the board. Now let's return to this side and start from that jobby here to the left. I turned the board so the left is now down here, and this is obviously a voltage regulator. To be exact, and I know some are upside down, it's an LP3962 ES-18. That's a low dropout LVO. Linear voltage regulator, 1.8 volts, 1.5 amps, and that's probably for supplying the DSPs that are up here. Then we have that little thing here. That's also upside down, and it's just a 74 LVC04A, a hex inverter. On the other side, we have a 25 megahertz oscillator, and beside it, a 74 LVT244K 3.3 volt 3-state 8-bit buffer line driver, obviously controlling some data lines going to the DSPs up there. Then we have a quartz 8192 hertz. And that is used by this microclock MK2049-34SI PLL clock synthesizer to synthesize clocks for ISDN, DSL and the whole stuff. The little thing beside it is a 74 LVT273DB. A 3.3 volt 8-bit D-type flip-flop, also controlling some data lines. The bigger thing beside it here is a 74 ABT244C, a 5 volt 3-state octal, so also 8-bit buffer line driver. So more communication lines going, in that direction here to the DSPs. Moving further down, or to the left in the overview, we have here two 74 ABT273Cs. These are 5 volt 8-bit or octal D-type flip-flops. Remember that thing? That was the same but for 3.3 volts. The little thing beside the two is a 74 LVT125, a 3.3 volt 3-state quad buffer. So we have here quite a mixture on this board between 3.3 volt and 5 volt data lines. Then we have here another oscillator, 16.384 megahertz. That's oddly specific. And then the elephant in the room. a Xilinx XC95144XL. That's a CLPD, so a complex programmable logic device. 144 microcells containing a total of 3,200 usable gates. So that's some kind of glue logic, keeping everything together. Moving even further to the left, that is down, we find here a Xilinx Spartan XC2S200. That's an FPGA, field programmable gate array, with 5,292 logic cells. A total of 200,000 gates, but that includes 56 kilobits of SRAM. And beside it, it's a little bit hard to read. Yeah, pause the video if you want to decipher that for yourself. That's an Infineon PXB4221E, an interworking element. That is, it connects 8 E1 lines that can carry up to 64 kilobit per second ISDN speech channels with up to 8 T1 lines. These are digital twisted pair lines and each can carry up to 1.544 megabits per second. And right below it we have a good old Samsung K7B40365B-QC75. That's 128K by 36 synchronous SRAM. Need for speed and storage, I guess. And of course we have another low dropout linear voltage regulator here. Same type, LP3962ES, but this time a -2.5 for 2.5 volts, 1.5 amps. We've just covered that whole section of the board, and now we will move to the back. One remark. Up to now we haven't seen a single microprocessor or microcontroller. Everything up to now was done by dedicated chips, DSPs, and some field programmable gate arrays and such. So not a single line of code involved up to now. I turned the board around 90 degrees again, so your bottom is the left and here's the edge of the board. That was the Samsung SRAM we just had a look at, and we have here another of those linear low dropout voltage regulators, 2.5 volts in that case. And here we have two AMD AM29LV160DB-90EC. These are 16 megabit flash memories, either organized at 2 megabit times 8 or 1 megabit times 18 bit. Right above them we have two 74 LVT16245 BDLs. These are 3.3 volt, 3-state, 16-bit transceivers. So we have somewhere a 32-bit bus going on. And right beside them is a 74 LVT244A. That's a 3.3 volt, 3-state octal buffer line driver. And above those we have 1, 2, 3, 4, 5 74 LVTH16244. So 3.3 volt, 16-bit, 3-state buffer line drivers. Yeah, a lot of line drivers, buffers and transceivers in that area. I guess that's interfacing to what's to come. So we just covered that block here. Now let's move on to the next block. Again, I turned the board around, so the bottom was the previous left in the overview. And first we have here two connection chips which work together. That GS3137-08-T and that GS2237-108 form together the DSL transceiver. Above those we have a 34.56 MHz oscillator. That's again pretty specific. And it probably supplies the clock signal to that Motorola XPC862PZP66 DSL communication controller. And then we have that little guy here. That's a Texas Instruments CD-CVF2505 PLL clock driver. I'm not quite sure if that also supports that chip or something else. And further up we have two Samsung K456416332F-TC75s. These are 4 meg by 16 SD RAMs, probably providing memory for that little thing down here. The last two chips in that block are either, because they don't have a complete number, 74LVT 244 3.3 volt 3-state octal buffer line drivers, or 74LVT 245s 3.3 volt 3-state transceivers. I can't say for sure. That was that block here, which obviously is dedicated to the DSL input. That leaves us with one last block to cover. Turned around the board again 90 degrees, you know the drill by now. This is our phone line / DSL line input. We have some protection diodes and a common mode choke of all things. And then we have here the DSL phone line isolation transformer that probably works in conjunction with that 0.47 microfarad capacitor. That thing seems to be a high precision resistor network. I'm not quite sure why that is used here. And further up we have our Ethernet connector, and accordingly that's our Ethernet isolation transformer. Close to that transformer we find an Intel LXT 970 AQB B11 Ethernet transceiver, 10 or 100 megabit. Above the Ethernet controller we have here first a 74 ABT273C. That's a 5 volt octal D-type flip-flop, and above it that's an ABT241A, a 3-state octal buffer line driver, 5 volt type. And then we have here 1, 2, 3, 4 SCLCDA12s. These are 4 bidirectional TVS diodes, 90 volts clamp voltage in one package. And then we have also here 1, 2 SCSRDA 70-4. That's 4 TSV diodes arrays, so 2 diodes in series, and you can access the middle point. These are used to clamp down data lines to ground and supply. And those are protecting, of course, the lines here on the X21 connector. And so it makes sense that this chip here, that's an LTC1543CG, is an X21 transceiver, but it doesn't support all X21 lines. The rest of the X21 lines is handled by that linear technology LTC 1545CG multi-protocol transceiver. Yeah, that thing is also multi-protocol, but here on that board they just do X21. In supporting roles, we have here first an 74 CBT 3125. That's a quad-FET bus switch. I mean, they spared no expense. FET switches, wow. That's a chip from Intel. That's a 24CO2N. That's a 2-wire or I2C 16K AEPROM, probably containing the code for our DSL communication controller right here. I mean, if that's its RAM, then this is its program ROM. By the way, that seems to be a bridge rectifier, and I have no idea why there is a bridge rectifier here on the board. You can clearly see the plus and minus markers on these pins. That's it for the front side of the board. So the telephone DSL line comes in here. Then we have these two chips which form the DSL transceiver. And that stuff here is the DSL communication controller. Then, after a lot of line drivers, buffers and some memory, we had here the Infineon interworking element, which probably separates all the different data streams on those E1 and T1 lines. I'm not 100% sure, but either from that interworking thingy or from the DSL communication controller, the thing goes back to the Ethernet controller and then out into our local network on that Ethernet connector. That is Internet does. The rest, that is ISDN data streams, go into our huge glue logic here with FPGAs and such and make their way over to our DSP section. And from there it goes to the ISDN subscriber controllers and out to the ISDN lines. Yeah, and we had, of course, power supply. Again, not a single microprocessor or microcontroller. All made with dedicated chips for specific tasks and a lot of glue logic. There's not much going on the back of the board, not even a lot of passives. We have here these 4-pin jobbies close to the ISDN connectors. Maybe these are additional protection diodes. We have a closer look in a second. Some 3-pin jobbies here, either transistors or protection diodes. And this is the only really interesting thing here, which has 8 pins. Well, no real surprises. That's also a TVS protection device. Internally, it looks like normal diodes building a bridge rectifier and then a TVS diode connecting plus and minus. Also protecting some input lines here, and that would be the telephone input line. The 8 other little buggers, I'm only showing 4 here, have marking 2 and then 35G. I came up empty, but they also have a plus and minus marking, which led me to the assumption on the front side that these are bridge rectifiers. But 8 more bridge rectifiers? No. I guess they are more like the other thing. We saw a bridge rectifier like protection diode arrays. That's it for today. I thought that would be a little fun, relaxing video, and then I was confronted with that. And you know me, I can't stop once I see these thingies. Anyway, we will return to our regular programming in the next video. Till then, bye.